In quantum mechanics, weak measurements are a type of quantum measurement that results in an observer obtaining very little information about the system on average, but also disturbs the state very little. From Busch's theorem, the system is necessarily disturbed by the measurement. In the literature, weak measurements are also known as unsharp, fuzzy, dull, noisy, approximate, and gentle measurements. Additionally, weak measurements are often confused with the distinct but related concept of the weak value. History. Weak measurements were first thought about in the context of weak, continuous measurements of quantum systems. The physics of continuous quantum measurements is as follows. Consider using an ancilla, e.g., a field or a current, to probe a quantum system. The interaction between the system and the probe correlates the two systems. Typically, the interaction only weakly correlates the system and ancilla. By measuring the ancilla and then using quantum measurement theory, the state of the system conditioned on the results of the measurement can be determined. In order to obtain a strong measurement, many ancilla must be coupled and then measured. In the limit where there is a continuum of ancilla, the measurement process becomes continuous in time. This process was described first by Menski, Belevkin, Barchielli, Lanz, Prospera, Barchielli, Caves and Milburn. Later on, Howard Carmichael and Howard M. Wiseman also made important contributions to the field. It should be noted that the notion of a weak measurement is often misattributed to Aharonov, Albert, and Weidman. In their article, they consider an example of a weak measurement and use it to motivate their definition of a weak value, which was defined for the first time in Ref. Mathematics. There is no universally accepted definition of a weak measurement. One approach is to declare a weak measurement to be a generalized measurement where some or all of the Krauss operators are close to the identity. The approach taken below is to interact two systems weakly and then measure one of them. After detailing this approach, we will illustrate it with examples. Weak interaction and ancilla coupled measurement. Consider a system which starts in the quantum state and an ancilla that starts in the state. The combined initial state is. These two systems interact via the Hamiltonian, which generates the time evolutions, whereas the interaction strength, which has units of. Assume a fixed interaction time and that is small, such that a series expansion of n gives, because it was only necessary to expand the unitary to a low order in perturbation theory. We say this is a weak interaction. Further, the fact that the unitary is predominantly the identity operator, as in a small, implies the state after the interaction is not radically different from the initial state. The combined state of the system after interaction is now. We perform a measurement on the ancilla to find out about the system. This is known as an ancilla coupled measurement. We will consider measurements in a basis such that the measurement action on both systems is described by the action of the projectors on the joint state. From quantum measurement theory, we know the conditional state after the measurement is where is a normalization factor for the wave function. Notice the ancilla system state records the outcome of the measurement. The object is an operator on the system Hilbert space and is called a Krauss operator. With respect to the Krauss operators, the post-measurement state of the combined system is the objects are elements of what is called a POVM and must obey so that the corresponding probabilities sum to unity. Doing so gives the conditional state of the primary system alone, which we still label by the outcome of the measurement. Indeed, these considerations allow one to derive a quantum trajectory. Example Krauss operators. We will use the canonical example of Gaussian Krauss operators given by Barchielli, Lanz, Prospera, and Caves and Milburn. Take where the position and momentum on both systems have the usual canonical commutation relation. Take the initial wave function of the ancilla to have a Gaussian distribution. The position wave function of the ancilla is the Krauss operators are, while the corresponding POVM elements are which obey. An alternative representation is often seen in the literature. Using this spectral representation of the position operator, we can write. Notice that that is, in a particular limit. These operators limit to a strong measurement of position. For other values of we refer to the measurement as finite strength, and as we say the measurement is weak. Information gain-disturbance trade-off. As stated above, Busch's theorem prevents a free lunch. There can be no information gain without disturbance. However, the trade-off between information gain and disturbance has been characterized by many authors, including Fuchs and Perez, Fuchsen, Jacobs, and Banashik. Recently, the information gain-disturbance trade-off relation has been examined in the context of what is called the gentle measurement lemma. Applications. Since the early days, it has been clear that the primary use of weak measurement would be for feedback control or adaptive measurements of quantum systems. Indeed, this motivated much of Belevkin's work. In an explicit example was given by Cabes and Milburn. An early application of an adaptive weak measurements was that of Dollar's receiver, which has been realized experimentally. Another interesting application of weak measurements is to use weak measurements followed by a unitary to synthesize other generalized measurements. Wiseman and Milburn's book is a good reference for many of the modern developments. Suggested further reading: Brunn's article, Jacobs and Steck's article, Quantum Measurement Theory and Its Applications. Jacobs, ISBN 9781107025486. Quantum Measurement and Control. M. Wiseman and G. J. Milburn. Tamir and Cohen's article.